Hello class, welcome to the STAT 211 lecture video on displaying and describing data. If you are following along with your textbook, this is going to be chapter 2.1 and chapter 2.2. Today we're going to cover two objectives. First, we're going to look at summarizing and displaying categorical data, and then we'll be looking at how to display quantitative variables. Most of what we are talking about today should be familiar with you, but let's look at it anyways. So if you recall, last class we discussed the difference between quantitative, categorical, and identifier variables. We also looked at how we can logically organize said variables. As a nice review, let's double check that we know how to identify quantitative, qualitative, and identifier variables. Order number is an identifier variable. It has numbers, but it is unique to each case or observation. Name, categorical variable. State, country, also a categorical variable. Price, that's going to be a quantitative variable. Area code, that's another identifier variable. Download, location, I see letters, categorical. Gift, yes or no, that would be another categorical. The ASIN, I'm going to assume that's an identifier variable. I'm not entirely sure what that is. I could look it up, but from what I know, from what I believe it is, that would be identifier variable. And artist, that would be another categorical variable. So overall, we have one quantitative variable and then quite a few categorical and identifier variables. Let's keep going. So visualizing data. So the problem with the data table is that we can't necessarily see what's going on. We might want to be able to see patterns, relationships, trends, and expectations. Some of the, or not expectations, excuse me, exceptions. Some of the easiest ways to do this is with a data visualization, meaning a graphical display. Because as great as this chart is, we may not be able to see trends in locations, pricing, artist, things of that nature that we might be interested in. So what do? We make a picture. There are 3 rules of data analysis, and that is simply make a picture, make a picture, make a picture. A picture will help you think clearly about the patterns and relationships that may be hiding in our data. And a well-designed visualization will show the important features and patterns in our data. And overall, the best way to tell others about your data is with a well-chosen picture. So again, when it comes to being able to understand the data, make a picture. Of course, there is always a caution that we need to say is when we are making pictures, we want to make sure that we aren't misleading our audience or violating the area principle. If we take a look at these 2 graphs, they look vastly different. The fact is, though, they're technically the same. They're the same data set. What we did is we changed the scale on the side. Notice on the left, we made our interest rates go up by 0.002%, whereas on the right, they were going up by 0.5%. So if we are looking at the graph on the left, we can see that interest rates have climbed. But if we were to look at it on the right, we would say that interest rates stayed about the same, which technically, prospectively, is both true. They have increased slightly if we're comparing it where 3% and 3.5% aren't significant, then we can say that it only increased slightly, but that change looks a lot more dramatic when we take a look at the graph on the left. So like I said, we don't want to violate the area principle, and we certainly don't want to be in the process of misleading people. The area principle is the area occupied by a part of the graph should correspond to the magnitude of the value it represents. So, for example, if we take a look at grade frequencies of an essay grade, notice that we have A, B, C, D, and F letter grades with the corresponding frequencies of 4, 7, 9, 3, and 2. So, in theory, we should have a corresponding amount of C frequencies, which is 9 out of 25, should be correspondingly recognized in our bar graph and our pie chart. To manipulate these areas to make them appear larger can definitely violate the area principle. If we go back to this graph, we had to notice that for the graph on the right, we started at 0% and went to 3.5%, whereas the graph on the left started at 3.14%. Changing the scale, changing the starting point, can be an issue with the area principle. This brings us to our first objective, how to summarize and display categorical variables. One way we like to start off with categorical variables is to display them in frequency tables, because they are easy to summarize in frequency tables because they list the number of cases in each category along with its name. Let's take a look at an example. A computer retailer compiles a list of the types of computers sold to the last 50 customers. So there were 4 types of computers sold: desktop, laptop, notebook, and tablet. Frequencies was 11 for desktop, 23 for laptop, 9 for notebook, and 7 for tablet. Let's try to have a better understanding of what this frequency table is telling us by understanding frequency distributions. A distribution is the way in which a variable's values are spread over all possible values. Discrete variables have values that are categories. The frequency of a category is the number of times it occurs in the data set. The frequency distribution is presented in a table that gives the frequency for each category. So frequency, number in the category, all together, frequency distribution. Sometimes we don't always look at a normal frequency table. Instead, sometimes we prefer to look at something called a relative frequency table. A relative frequency table displays percentages or proportions rather than counts in each category. Note, both of these tables show the distribution of the categorical variable, but each can provide us with different information. Sometimes a relative frequency distribution can provide us with better information as it relates to the whole than just the frequency. So let's take a look at our computer data set again. We know again that we have desktop, laptop, notebook, and tablet with a frequency of 11, 23, 9, and 7. So we can obviously see that more laptops were sold than anything else. But how much more of that constitutes our sales? Is it that much more than the desktop sales? Is the desktop and notebook sales from 11 to 9 really that extreme? Because frequency of 2 can be meaning a lot of different things when we compare it in terms of relative frequency. So in order to calculate relative frequency, it's pretty simple. We can divide by our total number. So each frequency divided by the total, in this case 11 over 50, 23 over 50, 9 over 50, and 7 over 50 will give us a decimal that we can then convert to a percentage. So we can either use the proportion value or the percentage. I don't know why, for some reason my brain likes percentages better. So if we take a look at percentages, we can see that 46% of laptops 46% of computers sold were laptops, whereas 22% were desktops, 18% were notebooks, and 14% were tablets. So if I am the manager of the store and I'm looking for ordering, I'm going to pay attention more to the percentages than I am perhaps to the frequency to know how many laptops, notebooks, desktops, and tablets I should order in the future. Let's take a look at another example. So in 2017, the CDC listed causes of death in the US. They provided percentages. Cause of death being heart disease, cancer, accidents, lung disease, and stroke, with their corresponding percentages. Part A, is it reasonable to conclude that heart or lung diseases were the cause of approximately 29.4% of deaths in 2017? Well, let's see. Heart and lung disease, Heart disease, 24.2%, lung disease, 5.2%. If I were to add those up, that would be 29.4%. So I'm going to say yes, that is reasonable to conclude. Part B, what percentage of deaths were from causes not listed here? All right, so let's think about this. What is the total percentage of causes of death? Hopefully you're thinking out of percentages, that's 100%. So for us, this would become a subtraction. So 100% minus 24.2 minus 21.9 minus 7.6 minus 5.2 minus 4.3 is 36.8%. So that tells us that the percentage of deaths that were from causes not listed below is 36.8%. Not bad. Let's take a look at a second example. Suppose we want to go ahead and convert into a relative frequency distribution. We've kind of seen how to do this already, but let's double check. So taking a look at this, we have data from the Titanic, and it's the number of passengers aboard. We can see that in first class we had 324, second class 284, third class 709, and then for crew we had 891. To calculate our relative frequency percent, we need to know the total number of passengers. So we'll take a quick addition. 324 plus 284 plus 709 plus 891 gives us a total of 2,208. From here, it's a simple matter of dividing. So divide each of these counts by our total. And then from there, we can change those decimals into percents. And we will get percent for first class being 14.67%, second class 12.86%, third class being 32.11%, and crew being 40.35%. Pretty easy. I can say this is something that you will be assessed on in your homework and will come up probably on quite a few of your exams or future assignments because we tend to look at tables quite a bit. Now, this seems to be an opportune time to tell you about a quirk that exists in Pearson. Let me remind you, Pearson is a computer system. It cannot read your mind. It can only understand things as they are given. what that means is that it is very important that you round your answers correctly and you give them in the correct format. If you do not do that, Pearson is going to mark your answer wrong. So if Pearson says you need to round to 3 decimal places, then if you round to 2 or 3, you're going to be in trouble. So let me say, for an example, suppose the correct answer for a question is 0.431. And generally in Pearson, when you're doing a homework problem or a quiz or exam question, there will be, after their answer, there'll be a parentheses, and a lot of times it is in red, and it'll say, round to 3 decimal places, or round to the nearest whole number, write as a simplified fraction. It'll tell you the format your answer should be given in. So if the correct answer is 0.431, if you do 43.1%, that's going to be marked wrong. If you give it as a fraction of 431 over 1,000, it's going to be incorrect. Around to 2 decimal places or 4 instead of 3, your answer is going to be marked incorrectly. Be aware, double check. On your homework, it's not a big deal because you can redo the problems, but on your quizzes and exams, it would be a shame for you to miss a point just because you rounded incorrectly. Okay, so as I mentioned, a big part of this lecture is talking about data visualizations. So now at this point, we're going to move on to talk about bar charts, pie charts, and ring charts. So a bar chart, also known as a bar graph, is a graphical representation of a frequency distribution. The bars are rectangles of equal width with one rectangle for each category. And as you can see, we have an example with the worldwide number of electric cars from the year 2012 to 2019. Again, notice that each bar is of equal width. There is a space between each bar, and each bar represents its own individual category. I'm assuming you are pretty familiar with bar graphs at this point in your education. One thing to be aware of, again, heights of the rectangles represent the frequencies or relative frequencies of the categories. Most important for you to understand with a bar graph is that they do have spaces between the bars. That'll become important here in a few minutes. There is a special case of bar graphs where categories are arranged in order from most frequent to least frequent, and this is called a Pareto graph. Just to give you an understanding what I mean with having a frequency bar graph and a relative frequency bar graph, notice these two graphs from our computer data set. The graphs look virtually identical. The only difference is on the y-axis where we have frequency and relative frequency. This should be the case where they look pretty much the same except for what's going on the y-axis. So be sure that you pay attention to what's going on your y-axis so you can make sure that you're interpreting your bar graphs correctly. So to show you what a Pareto chart looks like, again, it orders the bar graphs from greatest frequency to least frequency. They also frequently have a line graph that demonstrates the percentages as they go. So ideally, this first line is to demonstrate from that first 70%, and then as we go all the way up to 100% of the data. And I know I just said 70%, and that's not correct. 70% is or 70 is the frequency, relative frequencies here on the side. So actually, it's a little over 90% with this first bar, and then we peter off until we get all the way up to 100%. Another example, looking at office supplies and corresponding returns. Whoop, goes up to 100%. Again, notice the bars go from most to least. One side has the regular frequencies. On the right, we have the relative frequencies. So going back to the more familiar, we have pie charts. A pie chart is a circle divided such that each wedge represents the relative frequency of a particular category. For example, if a category has a relative frequency of 0.25, then its section, its wedge, its sector should take up 25% of your circle. Still using our computer sales data set, we can see it in pie chart format, where the tablet takes up 14%, notebook 18%, desktop 22%, and laptop 46%. Here's another pie chart. Little bit of a 3D formatting. A couple of things to talk about with pie charts and bar charts. One, you should know that any data that you use to make a bar chart can also be used to make a pie chart and vice versa. So again, any data you use to make a bar graph, you can use to make a pie chart. And note number 2, this is just, a little fun fact, but statisticians in general tend to hate pie charts as they are believed to be not good at communicating data. I personally don't mind them. I think they're effective at communicating parts of the whole, but if we're trying to compare parts to part, so if I'm trying to compare laptop to notebook or desktop to tablet, I think this bar graphs are pretty effective, but I think a pie chart is more effective when I'm trying to compare how much of the total sales are a particular object. But that's just me. But just warning you, if you come across other statisticians in your future, a lot of them do not care for pie charts. So last of these charts I want to talk about is the ring chart. It's also known as a donut chart. It is a modified form of a pie chart, but it only displays the crust of the pie. It is a ring that is partitioned into regions proportional in area to each value. Another way to think about it is if we were to take take the bars of a bar chart and then just stick them on the ends of each other and wrap them around so they form a circle. Here is some example of ring charts. Honestly, they are way easier to understand visually than try to explain orally. So here are 3 ring charts. First one shows the furniture sales as a percentage of overall sales. Next one shows office supplies as percent of overall sales, and then technology as percent in overall sales, where the highlighted portion represents the part of the whole. So 30%, 40%, 46%, and 27%. Here's another one saying what are the main greenhouse gases, and really a ring chart is pretty much just a pie chart. They just carved out the center in the end, But just so you're aware what they look like and how to interpret them, here we are. This now brings us to our second objective, displaying quantitative data. So we've already looked at displaying categorical data. Now we get to move on to quantitative data. So the whole concept of frequency distributions have not gone away, but we do have to make a little bit of adjustments. Because continuous data, or even, numeric data, doesn't have natural classes, or should I say categories, we divide them into classes ourselves. These classes are intervals of equal width that cover all values observed in the data set. So still using Titanic information, we could divide our age ranges. So the ranges of people aboard the Titanic spanned from 0 to 74. And so we could divide these classes into 5 years, 0 to 4, 5 to 9, 10 to 14, and so on. And basically, these classes become categories. It is important, though, that these classes are of equal width. So you couldn't make a class that goes from 0 to 9 and then 10 to 14, 15 to 25. They all need to be equal in order for them to be appropriate to graph with something, say, like a histogram. A histogram looks almost exactly like a bar graph. The only difference is that bar graphs are displaying categorical data, histograms display quantitative data. And because of this, there are no gaps between the bars unless there are 0 observations in the classes that we created. So again, histograms for quantitative, bar graphs for categorical. How can you tell the difference? Look to see if there are gaps or spaces between the bars. So one thing with histograms is we do have the ability to determine the bin width, which tells us how large our classes are, basically. Do we have each bin, each bar, 2 years, or do we make it 20 years or 4 years like we did here? It's up to us. Again, always try to be ethical and make sure you're not trying to manipulate or hide data, but you should pick the graph that is going to display data in the way that you're trying to present it. So if you're looking at something where you're just trying to say, what was the most common age of a passenger aboard the Titanic, then having the bins at 20 years might be more appropriate because you can easily see, okay, most passengers were between 20 and 40. We're trying to have a little more nuance and trying to see, peaks of highs and lows. We might find something like the 2 years more informative. The trick, of course, is trying to give accurate and clear information, but not overwhelm or make things too confusing to understand. Kind of think like models. They are a simplification of reality. Well, we want something that is clear and understandable, but not so complex that people are unable to use it or understand it effectively. So in addition to histograms, there are other graphical displays we can use with quantitative data. 2 of the most common ones are stem and leaf plots and dot plots. Here's an example of a stem and leaf plot. This is kind of a unique plot where each data value is split into a leaf, which is usually the last digit of a value, and the stem, which it corresponds to the other digits. So for us, how would we read this so the stems in this case would be the tens place and the leaves are the ones place. So we have numbers like 44, 46, 47, 49, 63, 81, 106. Notice that there are no numbers under the 5 and the 9. That means there was no data in the 50s and 90s. We can't skip those spaces. We do have to include them, but we just leave the leaves empty. The stems still exist. Let's take a look at a quick example. So we have a data set that's 45, 6, 9, 24, 45, 34, 39, 2, and 27. And we want to make this into a stem and leaf plot. No problem. So 0, 1, 2, 3, and 4. So we have a 2, a 6, and a 9. Yes, we need to put these in order from least to greatest. We don't have any 1s or 10s, I should say. So we'll go to, let's see, we've got 24 and 27. So 4, 7. Then for the 30s, we've got 34 and 39. And then we get to end with 2 45s. There we go. Easy. These types of displays are really nice when we're trying to really work with smaller data sets that we might want to do some computations like finding the minimum value, the maximum values, modes, things like that. They kind of look like histograms if you were to turn them over on their sides, but not exactly. The other type of graphs we have are dot plots. And dot plots place a dot along an axis for each case in the data. It is similar to a stem and leaf plot, but it uses dots instead of digits for the leaves. So, for example, if we have the number of minutes it takes to eat breakfast, we have the data set and we round it to the nearest minute. So in other words, we create classes or categories, and we simply have dots to correspond the number of people. So 6 people can eat in about 0 minutes. Probably means they either shovel it in one bite or don't eat breakfast at all. 2 people, 1 minute. 3 people can eat in 2 minutes, and so on. Again, in many ways, this kind of looks like a histogram where we can see the ebbs and flows of the data and gaps where people didn't exist in that situation, or people didn't eat in that amount of time. So at this point, we can go ahead and take a look at how we can create these graphs in StatCrunch. To begin, we're going to use the Getting to Know You data set. Actually, I take that back because I don't have the Getting to Know You data set, because this class is actually being taught in online format, so we're going to have to use a different data set instead. So let me go ahead and open up Pearson. So traditionally when I teach this class in person, I have an activity called Getting to Know You, and I ask it like 5 or 6 questions, and then I create a data set using that information. That's not going to apply this time, and that's okay, because it'll give us an opportunity to use some of our textbook data sets. So just to remind you how we open up Pearson, from eCampus, we go to Pearson's MyLab, go to Open MyLab and Mastering, and here we have our 211 page. I'm going to go ahead and select the option that says StatCrunch. And because this is our opportunity to work with data sets from our textbook, I'm going to go ahead and select that option. So because we're looking at Chapter 2, I'm going to go ahead and select that option. And let's see. Well, we've been looking a lot at the Titanic, so maybe let's do something else. Well, let's try cereals. Not as much categories as I wanted. I wanted to be able to have something that'll provide not only numeric data, but also categorical. We'll start with this one on acid rain, just to kind of give you some nice demonstrations. So this is the first time we've really looked at StatCrunch. So the first thing I want to show you how to do is just to get some basic summary information. So if we want to get that summary statistics, we can go to Stat, Summary Stat. Our data is given to us in columns, so we'll go with that. I'm going to select PH, because that's where the numbers are, and hit Compute. By doing so, I can get the summary statistics, the number of observations, the mean, the variance, standard deviation, standard error, median, range, minimum, maximum, quartile 1, and quartile 3. In case you missed it, I'll do that again. Stat, Summary Stat, Columns, select my column of interest, go to the bottom here and select Compute. Easy. Let's talk about how we can make some graphs. So next to the Stat option is the Graph option. And notice, look at all the options for graphs: bar plot, pie charts, chart, histogram, stem and leaf, box plot, scatter plot. It goes on. So pretty easy in StatCrunch. Like I said, this is some pretty point and click software. So for our continuous data, the pH, we're going to select histogram. Our numeric column is pH. Our frequency, relative frequency or density. We'll stick with frequency for the moment. We have it, we'll group it by date and hit compute. That didn't work the way I was expecting it to. Let's try that again. Oh, I see what happened. So each date, they created their own bar. Okay, fun. Let's try that again. Let's get rid of the group by and just hit compute. There we go. That's what I made the error on, was trying to group by date instead of letting it naturally group as it was supposed to. All right, so taking a look at this histogram, we have our frequency and our various pHs. If we wanted to make this a relative frequency histogram, we could go to Options, Edit, and just change the type from frequency to relative frequency. Compute. Again, looks pretty much identical, only our y-axis has the proportions as opposed to frequency count. All right, let's see if we can't find a data set that has more categorical data. Maybe might have to try something. Well, not exactly what I wanted, but we're going to go ahead and give this a try anyways. So, histogram, as I said before, you can go to graph, histogram, plug in your desired categories. For something like a pie chart or bar chart, same kind of idea. You go select graph. In this case, we have the data, score, compute. And in this case, like I said, it didn't work out exactly because I couldn't find true categorical data. I was hoping one of the pet data sets would work for us. Maybe I'll pause this video for a second and see if I can't find what I'm looking for. All right. Back in no time for you guys, and sadly the first data set I picked was the Titanic one because I knew it had categories, but I was trying to pick one that wasn't quite that. But let's go ahead and let us match by age of passenger to see if maybe we can't, next to it has classes and biological sex, and not to mention the categories that the people were in, ticket, fare, cabin numbers for some of them, where they join. So we have some nice categorical data we can actually graph here. So let's say bar plot with data. Let's see if we can. We'll start with class. So I'm going to hit compute, and here we have frequency by people, what class they were in, either first, second, third, or a member of the crew. If we want to do a bar chart, we can do that. Graph, pie chart with data. Again, I'm going to select class, compute. Here we are. First class, second class, third class, and crew. Pretty easy, particularly when you have a data set you can find. All right, so that was kind of the intro to StatCrunch I wanted to show you with. Let's see. I think that was just about it for what I wanted to talk about today. Yep, that's right. All right, so very good. Little pause on the end, but not too bad. So as always, though, if you have questions, send me an email. You're not going to have to make too many of these graphs in your homework, but you will need to be able to interpret them. So you should be good, but if not, like I said, ask questions. I'm here to help. Have a great night.